Hey guys, I'm Wyatt, and today I'm going to be walking you through OFRAC from setting up, configuring it, and playing around with binaries in the GUI. This is going to be a lot of fun. I'm super excited. First, want to make sure you have OFRAC on your system. So if you run ofrac-h or -help, you can see that it's installed. If you don't have it installed, you want to make sure you pip install OFRAC. So you can read about OFRAC on our website, ofrac.com. Pretty cool website here. OFRAC stands for the Open Firmware Readiness Analysis Console, and it's a tool you can use to unpack, analyze, modify, and repack binaries and firmware. And we like using it every day at Red Balloon.
Well, and also, Wyatt, who are you?
Oh, I'm Wyatt. I play with binaries at Red Balloon. I like to manipulate binaries, Oh, and I'm the product manager of OFRAC, which is why I'm making this video. Anyway, okay, let's jump into it. Okay, so if you run the help command, you can see the kind of commands you have here, and we've added a bunch of commands you can use to look at your OFRAC environment. The first one I'm going to show you is OFRAC list. So if we look at list can help show you all the packages you have installed. So if I run OFRAC list-p, I can see I only have the core OFRAC framework installed. If I look at -c, I can see all the components that I have installed in OFRAC here. I want to add in some disassembler components so I can look at disassembled binaries. So if I run pip install ofrac anger and then ofrac capstone, this will run and it'll install these bindings for anger and capstone, which are popular disassembly backends. And once we have them, we'll be able to disassemble things using OFRAC. These are not the only disassembly backends. We have a bunch of them actually in OFRAC.
Wyatt, which one is your favorite?
Oh, that's an interesting question.
You're on video. You have to say one answer, and
So I have to say, recently I've been having a lot of fun playing with. They're all good for different things. Okay, so if we run ofrac-list-p, we can see now that we have ofrac capstone, ofrac anger installed. So let's say we want to take a look at a binary in OFRAC. We can type ofrac GUI --backend anger, use the banger backend in this case, and then we can drag a file into here. So I'm going to look at this TinyCore ISO file. If you don't know what that is, you'll learn a little more as we explore it here. So here we have the general OFRAC GUI views.
What is it then? You should say it. What is TinyCore?
TinyCore, well, it's an operating system that is packaged in ISO that is, used to do things on computers. Yeah. So on the top left here, we have a bunch of different commands of things we can do in OFRAC to analyze things. The bottom left here, this is a view of everything that OFRAC knows about the file right now. So you can see it doesn't know much about it right now. But if I click identify here, we ran an OFRAC identifier against it and we learned a little more. So we can see it's an ISO 9660 CD-ROM file system data, DOS MBR boot sector, TinyCore. Cool. And then on the right here, we have a traditional hex edit view. And this is my favorite part of the GUI, this mini map over here. So what this mini map shows you, it shows you kind of a high level view of what's happening in the data. So I want to dig into a little more. So this entropy view right here shows you the entropy of the file. So you might ask, why? What is entropy? Well, if you go to our documentation on OFRAC, you can look inside the user guide, and then if you look inside the key concepts for the GUI, we have all this information about the minimap view. So you can learn, for example, what entropy is. The 10-second explanation is things that are white are very high entropy, which means there's a lot of randomness in the data, and things that are lower entropy are more structured. So this file looks like it's very high entropy. And so now we've identified it.
But what are some things that are high and low entropy? What is a high entropy thing?
Good question. So things that are high entropy usually are either compressed, so you can think like a zip archive, or sometimes things that are very, very, very high entropy are encrypted. So those are kind of things that are very high entropy. Code usually is not very high entropy uniform, so we know we're not looking at code right now. And so this ISO 966 image, the OFRAC docs actually have a little more information about it. But most importantly, we have an unpacker here that we can use to unpack it. So I'm going to go ahead and click the unpack button, and we're exploring it after we unpacked it. We have this thing called core.gz. So looking at the magnitude view, this looks like kind of random stuff. And if we look at the entropy view, wow, this looks like it's very high entropy uniform here. No surprise, this is gzip data. So gzip is another compression type, which is why it is high entropy. And we have an unpacker for that, so we can unpack it. And then if we look at this file here, look at this thing here. So it is a CPIO file system, and notice how the entropy is much different from the gzip before here. We can also switch over to the byte class view. So byte class is breaking down the binary into buckets based on the bytes that you're looking at. So all the bytes that are yellow are printable ASCII characters. The blue ones are below, the purple ones are above that range, and so on and so forth. And so we can basically see that this is kind of an interesting thing. And then we can unpack it here. So we're using our CPIO file system unpacker. Now we have the decompressed file system. And now what we can do is we can go in and look at an actual binary. So I'm going to look at this one. Oh yeah, look at this. So look at how the byte class view looks much different from the things we were looking at before. And now we can use the unpack recursively button. What this is going to do is it's going to unpack the file, which is an ELF, and then unpack all of the complex blocks and basic blocks and instructions within this file. So we're going to run that. It takes a little while to run because it's doing a lot of stuff. But once it does it, we will see this output, which in this case is being pulled from the Anger backend. But I could just easily have used Binary Ninja or Gija or anything else. Yeah, and so we can see here now we're looking in the ELF section, so this code region within the binary. And then here's the main function, so we can look at the disassembly here and even drill down and get the basic blocks and even pick out the instructions. So I've been poking around in the GUI a lot, but what's a really cool feature I'm excited to show you is the show script button. So when you click this show script button, we have all the things that I've been doing clicking around as a Python script. So OFRAC offers a GUI interface and also a Python interface. And so we can take the script and run it and reproduce exactly what I've been doing here. So you can see here that, we got the file, unpacked it, and then got the core GZ, unpacked it, and then went down and got the BLKID file here and unpacked it recursively. So yeah, that's pretty cool. Okay, so let's open the GUI up. So we have that open. I'm going to throw in a TinyCore ISO file in here, and we're going to identify it, then we can unpack it, and then we have this file in here that's called vmlinus here. So looking at the minimap view, it looks like there's a lot of high entropy in it. In the beginning, there's a little lower entropy areas, and it has this interesting MZ string at the beginning of it. Oh, it says, look at this, use a bootloader, remove disk and press any key to reboot. Okay, that file looks kind of cool. I want to take a look at it. So if we identify it here, we can see down here that OFRAC says it's a Linux kernel x86 boot executable BZ image. Interesting. And so this, I think, is showing you the power of exploring things within the OFRAC GUI. So I click unpack. The public version of OFRAC doesn't actually have an unpacker for BZ images, but we can use the tools that we pulled into OFRAC to learn more and kind of continue analyzing this file. So if I click the Analyze button here, what we're doing is running all of the analyzers that run against this specific type of binary, and we can look at the output results here. So one of the analyzers that we have in here is a binwalk analyzer, and so binwalk explores the file and looks for magic that suggests what types of things might be inside of it. And look at this, kind of interesting. At this offset in the file, binwalk recognized gzip compressed data. Oh, and it even says it was compressed from Unix. Okay, cool. Okay, so now that we have found this vmlinus file and we see that there's gzip data compressed at this offset, what we can do is we can grab that address here and use the carve child feature in the OFRAC GUI. So what we want to do is we want to carve a child out at that address and go to the end of the file. So I put the address in, and we can create child here. So now we can take a look at this file, and yeah, it looks like we grabbed something that's very high entropy, and if we run identify on it, we now see it gets tagged as gzip data, which is awesome because now we can run an unpacker on it. And then we look at this file here. Okay, this looks more like what we're looking for. So this actually is, you can tell by the magic here, but I'll just run the identifier out against it anyway. This is an ELF file, so this is actually the kernel within the BZ image. So we just, with a couple of clicks in the OFRAC GUI, have been able to carve that kernel out of this BZ image. And if we look at the show script button here, what do we have? We have a script that reproduces all of these steps that we've just taken. So what I'm going to do is I'm going to grab this script right now. I'm going to copy it over. Let's say I don't want to keep clicking through the GUI to get this file. I can then go over to create a new script over here. So I'm going to call this script.py, and then I can throw this script into here. And then This script, notice this is a generic OFRAC script. So I'm going to skip over this part for now. This is basically setting up what components OFRAC uses when it runs. So for now, we don't need any of these. We can just use the default one, so that's good. And then this OFRAC function runs. It creates a resource with the TinyCore ISO, and then it identifies it, unpacks it, then it gets this child here, gets the VM Linux, and then look at this. We run all of the analyzers here, and then we carve the child at these offsets. Then we get that child, we identify it, unpack it, and then we identify and unpack that child here. So now what I can do here is I can run await generic binary.flush to disk, and I'm going to call this carved elf. Okay. And now I should be able to come in here and run this script. So that ran really fast. And now if you look, we have this file here, carved elf, which if we run file on it is, ta-da, it's the carved elf we just copied out of there. So that's really cool. Now we have a script that can carve that elf out so we don't have to click through the GUI a lot. Here, I have another TinyCore file. So if we remember, I was running against the TinyCore 12.0. So let's try to run this file against the same script against the TinyCore 13.iso. Let's put 13 in here. If we try to run this, oh, it doesn't work. And that makes sense because actually this file here, the gzip data is at this address 3CAE. And if we look before, the other one was at 3AAE. Okay, so our script was very specific to this particular file. So what we want to do is we want to write something that's as generalizable as possible. So now we can take the script that the GUI generated for us and start abstracting it out so it can handle any type of file here. So we're going to start with this line here. So what we want to do here is we want to run the binwalk analyzer and grab the attributes that are created after it's run. So we run binwalk attributes equals await vlinus, and then we can run analyze directly and then ask it to create the binwalk attributes here. So all the binwalk attributes are is a class with an offset, dictionary of the offset to the data that's carved out of binwalk. Okay, cool. So now what we can do is we can try to grab the gzip offset out of there. So gzip offset equals none. If you look at the output of binwalk, we can see that the description says gzip compressed data here. So what we want to do is we want to write a nice simple loop for key value in binwalk attribute dot offsets dot items. If value starts with gzip compressed, then we want to say that the gzip offset is the key there, right? Then we want to break it out of this loop. Now we just want to make sure that we actually got an offset. So to assert that gzip offset is not none. All right, now I want to test this out real quick to make sure that I didn't fat finger anything. So I'll import this breakpoint here, and then we can run our script. Yep. Got to install IPDB. That'll be real quick. So if I rerun the script, okay, we hit the breakpoint, and then we can check. All right, we got our gzip offset here. Yep. And it matches what we have here. Okay, awesome, cool. So now let's continue writing the script. Gzip offset not none. And now what we want to do is we can then change this create child call, and instead of using the hard-coded offset, we want to use the offset that we got from the binwalk analyzer. Instead of the end range of the file, we can just get the file's length. So we await file gmlinux get data length. Okay, so we use the get data length here. Now what we want to do is we've carved out that gzip, so now we want to unpack that file. What we can do is we can get that child. So I think we think it's gzip data. So we run gzip data equals await file vmlinux get only child, because we know there's only one child of that file. And then we want to unpack that gzip data. So we run await gzip.unpack, and then we want to get the child, which we think is an elf. So we run elf equals await gzip data dot get only child. And now we want to save that elf file out to disk. So let's run this here. And we want to call it carved elf 13 because this is the other 13 file here. Okay? And there we go. This is our script. So now let's run it. And if we run it here, it completes. And we can see we have two different elf files here, carved elf and carved elf 13. And if we look at them, we see that they're different because they're different carved files from the thing. Okay, so now we have a script that can take any TinyCore ISO file, unpack it, and carve out the kernel elf in it. And then we can use that to do further analysis, modify, and then eventually repack it up. So now I've showed you the power of using the GUI to transition to automation using the Python scripts. So far we've been using the built-in components within OFRAC. So now I want to walk you through writing your own component here. I have this file right here, this component file that we can use as a little thing to get started. And what we've actually done is we've already written a component in some sense here. If we look at the code that we wrote here, we have this analyzer that analyzes the file, and then it gets an offset within it, and it unpacks it at that offset, and then carves out, gets an elf out of it. So what we can do is we can create a resource view here. So we'll call it vmlinas, this resource view. And we can write a little OFRAC unpacker that does this exact automation here. All right, a little bit of the nomenclature here. So OFRAC unpackers target specific resource views. So in this case, we want to write one that targets the vmlinas. We'll call this the vmlinas unpacker. We also codify here what types of resources that unpackers create. Our unpacker here creates gzip data, and let's just then go in and import that. And it also creates an elf because it carves an elf out. So this is what this means. Targets is what the unpacker targets. So we're targeting all vmlinas files. And then these are the outputs of the unpackers. In this case, gzip data and elf. Now we want to implement the unpacker itself. Okay, so now we can take this logic that we already wrote over here and carve it out and throw it into the unpacker. So we just want to change this to make it a resource. Then we want to make sure we have binwalk attributes imported. And then this is the resource, create child. And so here we know that the child is gzip data. So instead of just tagging a generic binary, we want to specify that it actually is gzip data here. And then we go from the gzip offset until the end of the resource here. So now we've created that child. Now the gzip data we want to get from the resource, and then we want to unpack it, and then we want to get the elf out of here. And I want to run an identifier against this elf to make sure it gets tagged as an elf. And then the last thing I want to do is I want to make sure that this worked correctly. So I'll add in a little assert that elf has tag elf. This way the unpacker will fail if anything messed up and this actually is an elf file. So yeah, just to walk through this again, we get the gzip offset from binwalk, then we carve the gzip data out of it at that address, we unpack the gzip, then we get the elf, and then we identify and make sure it actually is an elf. So we just wrote our first OFRAC unpacker. This is really exciting. So now what can we do? We can take this code here, and so this file is called component.py, so let's rename it to vmlinas.py. And what we can do now is we can use OFRAC's ability to discover new components. So what we want to do is we want to import vmlinas, and then what we want to run is run ofrac.discover vmlinas. What this command is going to do is it's going to look in this vmlinas file. It can also discover entire packages and find all of the components within this file and automatically register them so that they're exposed to OFRAC. So now we've done that, what we can do here is we can comment out this code here. So at this point, what we can do is we can add the tag to file vmlinas. This is telling OFRAC, all right, this is a vmlinas file. Let's just add an import up here from vmlinas, import vmlinas. And then we want to make sure that we save that so that the tag is flushed to the backend. And then what we can do here is we can run await file vmlinas.unpack, and then this will unpack it. And so what I want to do now is I want to break here and make sure that the changes that I made are correct. So here we can use this handy little tool called Open GUI. And what this does is it'll create a little kind of like a breakpoint within our program. So we can specify a host, a port, and a focus resource. So I'll use localhost for this, and then I'll use port 8080. And then we want to focus on this file VM-Linux resource. So I can run s equals await, and then we can just have the server run until it's canceled here. And this will pop up our GUI at this point in the script. Okay, so if I did everything correct, this is going to work. I mean, I did do everything correct. I don't make mistakes, so this is going to be awesome. All right, there, we saw our unpacker ran. Okay, so looking at our command line, we see the unpacker ran, and the GUI opens up, and ta-da, we have the VM-Linux, and we have the gzip data here, and we have the elf unpacked in here. So yeah, that's another really handy tool, the GUI. You can use it to set breakpoints to look at where you are in your script, kind of look at the files that you're manipulating there. So I just showed you how to run components in a script. So now I want to show you how to do the same thing, but from the GUI. So if we look at the ofrac GUI command, we have the backend flag, which I already showed you. But we can also specify imports. We can import the VM-Linux.py file here, and this will allow the OFRAC GUI to discover all the components in there and use it in the GUI automatically. We can also pass a file directly to the GUI. So we can use TinyCore ISO. When we run this command, this will open up in the GUI, and we can unpack here, drill down, come to our VM-Linux file, and here we can use the add tag feature in the GUI, and then we can add the VM-Linux tag right here. We can then run identify on it, and then we can run unpack. That will also unpack it here. Ta-da! Yay. I just showed you how you can write your own components in OFRAC and use them in OFRAC scripts, and even use them in the OFRAC GUI using the import and discover features to explore new custom unpackers and repacker components that you write yourselves. The power of using OFRAC to explore and modify binaries. And we didn't really modify things, I think, if you're calling me out, but I think in our next segment we're gonna look at how you can use this unpack stuff to modify things, to change the behavior. Cool.